there we go, graphing radical functions exploration, and then there is also a class kick over graphing radical functions that will need to be done sometime during today and tomorrow. To get started on the exploration, I've kind of just going to go through some of the graphs that you're going to need to do. You're going to do most of them on your own. However, just to kind of get the idea of what you need to do, I'm going to get you started. So going back a ways into our deep, dark memory, we did our Desmos project at the beginning of the year. We've also done graphing in previous units. We've transformed parent functions where we moved them left and right, up and down. We reflected all of that kind of stuff. We've done that with quadratics quite a bit and some other graphs as well. So just a reminder of what these parent functions look like, right? So we know that we had the absolute value of x. Okay, the absolute value of x would look like this, where we would have a point at 0, 0. And then if we filled out a quick little table of values, we would find that we would have, our graph would look like this, where we're coming out with a slope of -1/1 and coming out this way with a slope of +1/1. And they'd be coming to a sharp point. We've done some graphing with that with our Desmos project. We have also done a lot with quadratics. Okay, so remembering a quadratic has a curve to it. The parent function would be at 0, 0. And then if we made a quick table of values, if we had x is 1, we'd be at 1, -1, 1, 2, 2 squared would be 4, -2 squared would be 4, 3 squared would be 9, and -3 squared would be 9, and we would end up with, here would be our parent function. And if you remember, we've spent a lot of time with quadratics in vertex form, going back where we would have things like, when it was the vertex form was x minus h squared plus k, and we had a little a out in front, and every one of these numbers did something different to that parabola. Remember, the a value would shrink it or stretch it, it would reflect it if it was negative, the h would move it left and right, the k would move it up and down. These are things that we're going to be looking at again today. And then the graph of, that should be y equals, not x equals x cubed. X cubed would be a quick parent function of that would be at 0, 0. If x was 1, 1 cubed is 1. If x is 2, 2 cubed would be 8, so we'd be up here. X is -1, we'd be at -1, and -2 would be down here. And what it makes, and you can use Desmos if you want to see this a little more clearly, because you can use Desmos for this oops-a-daisy, that was supposed to be more of a straight line there, is that you have a graph that looks essentially like that, okay? So by knowing the graph of the parent function, remember, we've done a lot of this with quadratics, we know how if we put numbers with the parent function, it'll move things left, right, up, down, reflect, shrink, stretch, all that good stuff. So that's what we're going to be focusing on today. Except this time, we're not doing absolute value x squared or x cubed. We are going to be doing square root functions and cube root functions. So those are the two things we're going to focus on today. Okay, so over the course of class today and tomorrow, you are going to work your way through this graphing radical functions. Okay, so let's just do a quick look at the parent function for a square root, okay? And so I made a quick table of values over here. We're going to complete that. We're going to use this as our formula. Y equals the square root of x. So if x equals 0, right, y would equal the square root of 0, which is just 0. So one of our ordered pairs is at 0, 0. If x is 1, the square root of 1 is just 1, so we'd be at 1, 1. X equals 4, the square root of 4 equals 2, so we would be at 1, 2, 3, 4, 1, 2. And then if x equals 9, the square root of 9, square root of 9 would equal 3. And notice, 1, 2, 3. I did not have any negative values for x, okay, because we are in the real number system, which means if we had, if x was to equal -1, we would end up with the square root of -1, which is an imaginary number. And when we are graphing on the coordinate plane, we do not have imaginary numbers that we can just easily graph. So we are sticking in the positive domain, which means our graph is going to go like this. It's going to have a soft curve to it, and it's going to keep gradually going up just a little bit, okay? We are actually going to skip talking about domain. We're not going to worry about domain too much right now. And we're going to focus on what happens when we put numbers with our graph, or excuse me, with our parent function. So every time, what you should do, just sketch a quick, we're in square root, so we're going to do a quick sketch of our parent function. So our parent function was the one that we had above. So we're going to be at 0, 0, 1, 1, 4, 2, and 9, 3. If you want to copy and paste that on all of the square root ones, you can do that. And it's kind of nice if you can actually, let me zoom in here, see these ordered pairs, because when we go to compare our parent function to the one that we are going to look at, it's ideal if we have the ordered pairs that we can see and easily see what our new graph is going to look like also. So we have the square root of x minus 4. Okay, so again, I strategically chose the numbers that are in the x column so that we would get whole number answers. Okay, so if I have x equals 4, that means I'm going to have the square root of 4 minus 4, which is the square root of 0, which is 0. Okay, I'll plug in all of the ordered pairs here in a second. If x equals 5, the square root of 5 minus 4, again, I'm just using this equation up here. 5 minus 4 is 1, the square root of 1 is 1. The square root of 8 minus 4, 8 minus 4 is 4, square root of 4 is 2. 13, the square root of 13 minus 4, 13 minus 4 is 9, square root of 9 is 3. So when I plot these over here on my graph, right next to my red parent function, I'm going to be at 4, 0. Okay, so I'm going to be at 1, 2, 3, 4, 0. And then I am going to be at 5, 1, 5, 1. And then the only other one that's probably going to fit on my graph is going to be 8, 2. So we're going to be at 8, 2. And again, we can't fit that last one on there. But if you notice, what has happened with from our red graph to our blue graph is that we have shifted 4 units, every one of these graphs, every one of these ordered pairs, 1, 2, 3, 4. Here's this point, 1, 2, 3, 4. Here's this point, 1, 2, 3, 4. And if we would have had a bigger graph, we could have actually seen that with the last point as well. So when we have an x minus 4, so the square root of x minus 4 means that my graph moved to the right 4 units. So we would just say describe the transformation is just right 4. Okay, so we're just going to do our ordered pairs in our table of values and sketch a graph on just a whole bunch of different graphs here. Okay, this next one, it's the same basic idea. I'm not going to do it for you, but I do want to make sure, put your parent function to start with, 1, 2, 3, 4. Put your parent function on the graph so you can see the ordered pairs first. Again, if you want to copy and paste it onto all of the square root ones, please feel free to do so, okay? And then what you're going to see is when you fill out your table of values here and sketch your new graph, you should be able to describe exactly what's going on with it, okay? And then, again, keep working through them. The square root of x minus 7, if you notice, this minus 7 is not underneath of the radical, like the one above it, the x plus 2 up here. The plus 2 is under the radical. The minus 7 is not under the radical, which means it's going to, so like, for instance, x equals 0, the square root of 0 minus 7, 0 minus 7 is negative 7. The square root of 1 is 1, minus 7 is negative 6. So you're not going to subtract 7 and then take the square root. You take the square root and then subtract 7. Okay, and again, just like every single time, copy, paste all of your parent function first. It just makes it easiest that way to see what the transformation actually is. Okay, and then again, you've got another one with a 3 on the outside where you're going to test and see what that is. Again, always making sure you put your, oops, I think I put that in the wrong spot. Always putting your, there we go, parent function on there first, okay? Again, this one has got a decimal out in front that you're going to need to figure out what that actually does to your graph. This one has a whole number out in front. What's that going to do to your graph? This one has a negative out in front. What's that going to do to your graph? Every one of these should have the parent function and the new graph on the coordinate plane, okay? All right, so then we're going to do the same thing, except this time it's going to be a cube root function, okay? So the first thing we want to do is use Desmos or whatever it is that you want to use to figure out what the cube root parent function actually looks like. And then we're just going to go through that same process of looking at the graphs, seeing what numbers underneath of the radical do, outside of the radical do, added or subtracted, out in front, all that good stuff. So parent function first, right? And again, I strategically chose these x values so that we would have whole number, nice ordered pairs. The cube root, okay, so again, if x equals -8, the cube root of -8 is -2, because -2 times -2 times -2, 4 times -2 is -8. Okay, so we have a negative that we're taking a cube root of. The answer is going to be negative. And then we'd have the cube root of, oops, daisies. The cube root of -1 is -1. The cube root of 0 is just 0. The cube root of +1 is 1. And the cube root of +8 is +2. So what this graph is going to do, the curve is going to look like, we'd be at -8, -2. That's going to be down here. -1, -1, 0, 0, +1, +1, and then +8, +2. And what the curve does is it comes through, it does a nice soft curve, and comes back out on the other side. Okay, so that's your parent function. Go ahead and copy and paste it onto all of your graphs really quick if you want to, if that's going to make it easier for you, so you don't forget to do that. And then we have, oops, there should be a y equals. This should have a y equals the cube root of x minus 3. And you're going to do, again, I strategically chose numbers over here so that it would be easy to figure out nice ordered pairs for you. So we would have the cube root of -5 minus 3, the cube root of -8, which is -2. And go ahead and finish out here. So we're going to have the cube root of 2 minus 3 is -1. Cube root of -1 is -1. The cube root of 3 minus 3 is 0. Cube root of 0 is 0. And so on. So you end up at -5, -2. So let's make sure before I do anything else, I am going to put my parent function on here. Okay, got my parent function. Bloop, there it goes, like that. And now I'm going to graph my function that has an x minus 3. So I'd be at -5, -2. 1, 2, 3, 4, 5, 1, 2, -5, -2, 2, -1 here. And then I'm at 3, 0, 1, 2, 3, 0, and then I'm at 4, 1, and then I can't quite get to 11, 2, because that would be out here. But when I go to sketch that, it's going to look very similar to the other one, except if you notice every one of these points, in this case, is moved 1, 2, 3. This point is moved 1, 2, 3 to the right. This point, 1, 2, 3 to the right. This point, 1, 2, 3 to the right, and so on, which means just like with the square root, you have the same thing that it's going to do. -3 underneath of the radical means that we are going to move all of our ordered pairs right 3. Okay, and again, we're just going to practice that same idea with cube roots for multiple different types of graphs. So let's take a look a little bit further. Okay, and again, notice this one has the +5 is on the outside. So when you take the cube root of -8 and then you add 5, so you'd have -2. The cube root of -8 is -2. -2 plus 5 is 3. So just being careful with your order of operations there. Go ahead and finish that one. Put your parent function and the other function on there. Okay, and then this time it's just got a number out in front. What's that going to make your graph do? do your parent function, do your table of values and figure it out. Again, this one has just got a decimal out in front, and this one has a negative out in front. So go ahead and finish all of these. Any of them that I did not do, you should be doing on your own. Go back and finish them. You have time. Okay, so go back and do these ones as well. Again, with the parent function and the new function on the same graph so you can easily see. And then you need to do some conclusions here. Okay, these are going to be the same basic ideas that we had with a quadratic. What I'm looking for is in here, left, right, up, down, squish, shrink, stretch, reflect, that kind of a thing is the words that we should be looking there. And then without using Desmos or anything like that, or you probably don't even need to use a table of values necessarily. You can if you want to. Do a sketch of the parent function and sketch this graph, okay? And then how did we get there? What did we do? What did this +3 tell us to do? What did this -1 tell us to do? That's where we do the describing the transformations, okay? And then I believe there's one more on the last page. Yep. So then basically you're gonna sketch the graph. What did that negative in front do? What did this minus in front here do? And then what did this +2 here do? So analyzing the equation so you can write the graph based on the parent function, and you can describe those transformations here as well. So once you get these done, this entire packet, you need to make sure that you submit this packet, okay? And there is also a class kick that you need to complete over this content. Thank you very much.